Hi guys, welcome to Learn Electronics Repair and part 2 of how to repair switch mode power supplies without blowing them up. So in part 1 we looked at the theory of this, we looked at situations where you could put new MOSFETs in the power supply because they're short, only to find that when you plug it in, even with a current limiting light bulb, it blows up again. So this video is to follow on from that one, and this is the practical side. Now I have a favour to ask you guys. So the favour is, please do not comment on this video until you've seen all of it. The reason being, this is a very good example of the way I tend to work. So I'm tracing through a power supply. I don't have any schematics. I don't know exactly how this is connected up. And what I tend to do in that situation is make various assumptions based on prior knowledge and experience of power supply repair or whatever I'm working on. And we can go round to see if I can figure out how this particular one actually works. Now, often I will get that wrong, or I'll get it partially right, and then having taken some readings and observations, I may well revisit and think, actually, Richard, you were wrong. And this is a prime example. So you guys may be quicker than me on this one, and you may be saying, Rich, you're wrong with this, or Rich, you're wrong with that. Watch it all first, because you may find I change my mind later on. Okay, so enough said about that. Let's go. So here are our MOSFETs. Oh, that means 46 ohms to the gate in either direction. And it's short drain to source. And this one is just short. Yeah, that's just short. Okay, so on the power supply, this is our bridge rectifier. You can see like a little chamfer there. So this will be the positive leg. Okay, so from there to the main capacitor. Sorry, there's too much glare on there. You can see it now. Okay, that's the positive end of this one, and then the negative of this one goes to the positive of the other one, there to there, and then the negative of this one goes back to the bridge rectifier. These are those two high value resistors I mentioned, by the way. They're 100k each, which is just balancing the capacitors. Then we have from the positive end to drain of that one, source, I think it's here, source of this one to drain of that one, and then source of this one to the negative of there. So that's your path through your two switching MOSFETs. You notice I just roughed that up a little bit when I was unsoldering. This is what happens when you repeatedly fit and remove components. So I'll try not to do that anything much more than I have to. Right, so we have some resistors here. 103, so that is 10k, and 470, so that's not 470 ohms, it's 47 and no more zeros, so that's 47 ohms. Okay, I need to test these. If any have failed, it should most likely be the low value one. Let's have a look. So we'll go to ohms, and that is 47.6. That is basically the same. The 10k. Oh, that reads 1.1, but it won't be the resistor. I bet this will be the same. Resistors really don't fail by going low in value. What that will be, I'm sure, is the drive. So this is the secondaries of the transformer that drive the gates. Two separate secondaries by the looks of it, so those are connected directly to the resistor. Yeah, so that resistor is across there. So we have two different secondaries, not how I drew it on my diagram, but I did say that wasn't really accurate. So that comes to here, and then from there to there. I can't test these two 10k resistors in circuit. I have to unsolder them, but I will, because I need to be sure these are good. Okay, and then we have this little group of components here. So This is one of the AC pins. That's a diode, D15. So that comes through a diode. Oh, and then we have a Zener diode there. So we have some 100k resistors. This must put a voltage on here, actually. Let's have a quick look. Okay, so positive in. Diode is okay. The Zener. Yeah, it reads 714. Zeners in the forward direction always read a bit higher than a normal silicon diode. It works in the opposite direction as a Zener. Then we have a 100k. Yeah, it reads 100k. Another one. It reads 105. It's close enough. These in series. Yeah, they're in series with each other. That's a capacitor which is behind the large ones. That's that one. So those charge this capacitor up. Then you would assume that this being the positive end of the capacitor, via another resistor, possibly this one. See, so 47k. Does this go to this? Not that end. Yeah, that end. So 47k. That'll go to the Zener diode. So this generates a fixed voltage on here. And then this is the ground end, if you like, of the Zener. So that will go, looks like the emitter of this transistor. Is this bipolar? Put it back into diode mode. Let's have a look. Yeah, so yeah, base emitter. Sorry, base emitter there. This is base collector. And the other one doesn't read. Could be a PNP. Let's just go the opposite way around. So black on here. Yeah, that's PNP. That's PNP. And then we have one more resistor here, which is 4.7k. I suspect that this little supply here effectively powers up that chip. Yeah, most likely. We can probably trace, or certainly powers up these transistors which are driving the little transformer, and probably maybe powers that as well. We can have a look. We can actually test these transistors. I built the little $1 transistor tester. I actually took it apart because I'm waiting for a switch in a little enclosure. But you can do this with just 2 multimeters, preferably if you have a friend. And I believe I have a friend here at the moment. So, do I have a friend back there? There, he's laughing. So this is Detlef. I can't do this with my 2 hands, but between us we can. So Detlef.
Oh, there are people out there. Hey guys.
Yeah, people like that. Look over there.
Yeah, oh, yeah. Loads of them. Hey.
Loads of them. In fact, they're up here, look.
I should look there.
Yeah, I moved it. Okay, so what we're going to do is, this is an NPN transistor.
All right.
So I'm going to put the first multimeter, the fluke, on diode mode, and I'm going to connect it between the base and the emitter. Okay.
All right.
Which you'll see as a junction. Mm-hmm. What I'd like you to do is put your red lead on there and your black lead on the emitter. So you get in there, everybody can see the meters, it's fine. But they can't see that anymore.
Okay, get my red lead on there.
The only problem is with that, Det, you've got your head in front of the camera.
Oh, got it. Oh my God. Okay, sorry.
You can see it on screen here. Okay, so that's the collector. Mm-hmm. And then the emitter is that one.
The upper one or the lower?
Lower.
Lower one. Okay.
So that is measuring across the transistor. Okay. And then I'm going to connect between...
I better open here.
Well, yes, you will, because the transistor is switched off.
True.
So I'm now going to come onto the emitter of the transistor with you, yeah, and put this on the base and switch it on. And look what's happened to the multimeter. It's gone to 0. See that again?
Yeah, that goes.
So it switches on. Now the other one is a PNP, so we have to do this opposite way around. That's the one just below it. So you go with the black to the collector, red to the emitter being the bottom one, and I do the same from the base. So I'm going
to try to get this a bit more
over
there, so you have a bit more space for the probe.
Okay, so I come in here as well.
Yeah, I should be on.
And then, oh sorry, I need to put the red, the same as you, it's PNP. So we need to put the red onto the emitter and the black onto the base.
Yeah.
And it's switched on. Okay, guys, that's how we test those transistors in circuits.
And this is why electronic people need 3 hands.
Stuff with Babel Brooks.
This is why electronic people need a friend.
Oh, a friend, yeah. That could work
That could work too. Cheers, Dad.
Bye, guys.
We know that this circuitry here is okay then. There's another resistor here, 4K7. Does that work? Yeah, that reads okay as well. Are either the emitter or collector of these going to ground? Let's have a look. So the emitter of this one goes to ground. That's an NPN. That basically makes sense. This one, possibly the collector's going to ground. No. No, not going to ground. So it looks like, just looking at this, yeah, the base of that one comes from here. Is this driven from this one? Yeah, looks like that's driving that one. So it looks like here, neither the collector nor emitter go to ground. This is probably like a serial regulator, emitter follower type circuit, which comes over here. I'm pretty confident that that is powering this lot one way or another. Let's look at the data sheet for this one. Okay, so output A, output B, this drives the 2 transistors, oscillator output, timing components, voltage ref, this is for feedback inputs, where is it? Power, yeah, VC, so this is your power supply on pin 13, okay? There's probably a typical application. Yeah, it's sideways, but there is one. So this is a VREF, reference regulator. That's an output, that voltage. No, this is VC. This is the voltage to the collectors of the output transistors, basically. Yeah. Looks like this is supply on pin 15 plus VI. Let's have a look. Here, VI supply voltage, VC collector supply voltage. I was correct about that actually. So this is your supply on pin 15, okay? But it may well be the same on pin 13. Pin 15, does that come? That comes from there, okay? And 13, yeah, they're both connected to here. So this is where your supply is coming in. So we could try powering this chip up, but I'm pretty much assuming that the supply from here is also supplying these transistors. Somewhere. Maybe not. Maybe something else applies those. But what I'm thinking is, if we apply some voltage here to this capacitor, okay, then that through the resistor, this one feeds to the Zener. So if we put some voltage on here with our bench power supply with reference to hot ground, which is there, and we gradually increase the voltage on the power supply, we should be able to get the voltage here to stabilize. That's the Zener voltage. And we now then will have the correct voltage into this lot, so we can have a poke around in here. We can look with our oscilloscope to see, is this running, and to see, is this actually driving the transformers. I think that's what we'll do next. I'll still remember I do want to check those 2 resistors, by the way. But I will say, in actual fact, I find it very difficult to see how these resistors would fail due to anything going short in these MOSFETs because they're connected directly across the winding. So really, I don't see much opportunity of enough voltage getting across these to even damage them. Okay. So we will connect our bench power supply from here, which is the end of the resistor feeding the Zener. Okay. And the other end can go to here. This is actually hot ground. Okay. It looks like this end of the Zener doesn't go to ground. That goes to the base of here. This goes to ground. So it looks like that Zener effectively puts a voltage on the base of here. And then the collector of this will probably via a resistor. Put a voltage on the base of that one, and this is how the supply actually works, okay? In on the emitter, out on the collector. This is like an emitter follower type thing. This will get some voltage from somewhere. Not there, so I'm not sure exactly where this gets its supply from. So that might be interesting to see if this comes from somewhere else. But first of all, let's get the voltage in here first, and then we can have a look. What we can say is that the capacitor is rated at 50 volts, so the voltage is less than that, okay? I have two power supplies. One is just a 30 volt and the other one's a dual 30, which will go to 60. So we'll try the 30 volt first. If we can't get enough voltage into our Zener, then we'll go with the other power supply. We're all connected up. Then let's switch the power supply on. So at the moment I have this set down to 1 volt. I'm reading about 1 volt across the Zener. If I turn the power supply up, the voltage on the Zener is increasing at the same time. You can see that 12 volts, 12 volts. So I need to continue to increase the power supply until the voltage across the Zener stops increasing. I'm expecting it to be somewhere in the region of 20 to 30 volts, something like that. I'm not sure I'll get the power supply high enough on here. Let's have a look. So we'll keep turning it up. 28, 29, 30. Oh, and look, just as I got to the top, 30, so I'll come up again. That's on 30 now, the Zener voltage on the multimeter. And I can turn the voltage up here and it stopped following. I'm up to 32.2 now, and it stops at 30. I'll come back down, you see it's dropped down again. So that is a 30 volt Zener, which ties in very well with what we know about the voltage of the capacitor. Let's see if we've got any supply now on our chips. I'll take another multimeter. I could have used the same one, but hey, I've got more than one multimeter, yeah. I'll connect ground to hot ground over here. Bear in mind there's no main switch on at the moment on this. This is pin 15. And I don't have any supply. I have about 3.3 volts. Now we know that comes through here, so this is the voltage coming out, 3.3. This is the voltage on the Zener, we know that. So I don't have any voltage on here. Here is practically zero. This is the voltage we know goes out into this slot, and that's the voltage coming in. So we don't have any significant amount of voltage coming in here. I'm pretty sure this is effectively the emitter follower type circuit. So the Zener sets the voltage, but this actually provides the power to this. So let's have a quick look to see if I can figure out where this comes from. Alternatively, I could just try to power this chip up directly. But the problem I have really, I want to power this whole circuit up so I can see whether this is driving the transformer, okay? So let's just go a bit further down and see if we can figure out what voltage should be on here. Where does this come from? Well, we have what appears to be another type of power supply down here. So we have another Zener diode. We have a transistor, another transistor, so that's this one and this one. Then there's a third one, which is there. Okay, this pointer's ground, I know that. This connection here, that actually goes to the voltage selector switch on the metal panel, the front panel of this amplifier. So this is power in mains, this is the voltage selector, and this, does that connect to that thing? Yeah, that point connects into that. That's not ground, is it? Yeah, no, it's not ground. So this seems to be something to do with the voltage selector. Two high value resistance and this again. Okay, we can have a quick look around here. So we have Zener diode. Reads okay, 0.711. This is AC. Okay, this is AC, the voltage selector, I'm sure. Could be wrong about that, but I think this is AC. Doesn't connect directly into there though. Okay. You can see this is the positive end of the Zener. You can see the stripe on it. So that's your normal Zener direction. This is the forward direction. Yeah, so it reads 0.71. So that's what you'd expect, 0.72. This one, 0.49. Same, well, similar. And then we have a few resistors. Then we have these transistors down here. So let's have a quick look. That reads like a junction. That reads like a junction. So this could be the base in the middle. Okay. Then this one could be the base on this end. Let's have a quick look. Reads like a transistor. Reads like a transistor. Then we have the other one. Reads lower than you'd expect for a transistor. Let's see what that device is. That might not be a transistor. It might be a voltage regulator. Can't easily see down there. Try with a microscope. Yeah. 7812. That's a 12 volt regulator, okay? So we have another power supply for some reason here. Okay. And the technique we've used hasn't really helped us. I mean, we got the right supply onto here, 30 volts. I'm pretty sure that should supply this. Quite possible that this one supplies into here. I don't know. It's obviously doing something. So it's a little bit tricky without a lot of reverse engineering to figure out how to power this up with the bench power supply. Therefore, I think I'll go with the plan B, which is to leave the MOSFETs out and power this up and then see what it does. Okay, so I've disconnected the wires. I've just left this one on. This is hot ground. I don't generally like probing around on things like this when they're connected to the mains, because you quite easily get your fingers onto the board or something will slip and something will happen. I find it's much safer just to tag a wire on where you want and then take your hands off this while you take the reading. This is down to a personal comfort level, I think, really, with what you're happy with doing and what you're not. So the first thing I want to know is, do we have a supply on 15 volts, which is here, which is there, that capacitor. And the other thing I really want to know is, what do we have on here? Ah, that goes to there. So that is the voltage coming out of here, is definitely the supply for this. Okay, there, we know that now. I don't mind probing this while it's powered up because, to be quite honest, my finger's a long way away from it and it's not too easy to slip. So I'm expecting to have 30 volts on here, okay, and something more on there. I'm thinking 30 because it's a 30 volt Zener. There's some transistor in the circuit which might drop 0.6 or something, so it might be a little bit less than that. Once I reconnected the cables to here and then plugged the power lead into this, it's all a bit of a strange angle. It's difficult to get this to sit flat and measure. So in fact I've actually just tagged the wire on there. Okay. It's probably safer than trying to probe this because the thing's waggling around and I can't easily stop it. So this is probably the best way, but guys, whatever works for you, yeah. And the order in which we make these tests, like I was using the bench power supply first, I found that it wasn't that easy to power up in isolation, this chip. It's just one of those things, you don't know what's going to happen until you try. I've put the current limiting light bulb back in. You can see that over there. Now without the MOSFETs in, I would seriously expect this just to go bright as the large capacitors charge and then go dim. Just bear in mind, by the way, when you do something like this without the MOSFETs in, there's nothing to discharge the capacitors. So even when we switch this off, those will hold quite a nasty voltage until you either wait for these resistors to discharge them or you discharge them yourself, okay? Not with your finger, preferably, all right? Now let's power it up and see what happens. Bright, then dim and off, okay? And we have about 7 or 8 volts. That's all we have. And I don't think that is enough for that chip. In fact, was it 7 or 8 or was it... Yeah, about 7 volts. Something's discharging the capacitors, by the way, because that drops away pretty much straight away. Let's have a look what's in these big capacitors. 28 volts. 236 volts. So they're not even balancing, actually. Okay, that suggests that the junction between these two capacitors is what's providing the power into that, and something's drawing some power. So something is very wrong here, because this capacitor on this end has, well, 185 now. This has only 25, which is the same as that point. This has 0, of course. This is ground. 165. So these two capacitors are not charging up anything like equally. The only reason I can think of that is one, that one of them has a very high load across it, but then the light bulb would come on and stay on, I would have thought. Or the other case is that one of these capacitors is faulty, maybe. Let's wait till they discharge and let's have a look. Okay, I actually discharged the capacitors. This is a power resistor I keep for this purpose. It's a 3K3. Okay, that will happily discharge these things without causing any sparks or stress to the capacitor. Don't put your screwdriver across them, okay? It's dramatic, but it's not good. So 0.6 of a volt, 0.198. I mean, it's very difficult to get rid of the last bit. I mean, now you can short it. Yeah, because there's so little voltage in there anyway. Yep, it's gone now. Right, so we have two large electrolytic capacitors in series from the HT to ground, and one has 200 and odd volts in it, even though it's only a 200 volt capacitor, and the other one has about 25 volts in it, when they should both have the same. And there's two balancing resistors in here as well, which should keep them both the same. Okay, so there's only really two reasons for that I can think of. One is that the bottom capacitor has something else connected, like the junction of the two, and there's a heavy load on that one. Well, the MOSFETs return back to there via the transformer, so yes, the transformer does connect back to there, and it does so by passing through that large high voltage capacitor we looked at. That one. But I think if there was any current path, the other capacitor would explode. I mean, it's way over its rated voltage, as we could see. I think more likely the other capacitor isn't holding a charge. I don't think that's short. We can just check it. I think if this was short, we would know about it. But there is something drastically wrong with this. We also do know that. Well, it's reading a negative resistance. I almost certainly still have some charge in these capacitors. Enough so to do that. Okay, try again. Could be some charge in this capacitor itself as well. Or some other capacitor. Yeah, it's resistance, that's not volts. It's going very high, 15 meg, 17, 18 meg. So that isn't short. What do I read across these capacitors? So positive. Well, we're into the mega ohms and it's charging up. Okay. And the other one, positive to this end. Reads even more mega ohms. Yeah, that one reads a lot more mega ohms. I wonder, is that bottom one faulty? We should be able to test these in circuit. Because we have effectively nothing connecting the junction to anywhere else, it should just go to the high voltage capacitor. But something else could be being powered from there, by the way. I mean, we don't know where this lot effectively gets its power. It could effectively come from the junction of these two capacitors. I don't see why it couldn't. Okay. Well, let's see if we can measure them in circuit. So this is the positive end, negative end. That is 580. This one about the same. So from what I see, they both read about the same. Let's see if the resistance here to hot ground tells us anything. So this is the junction, so we go from here to hot ground. Effectively reads open. Okay, meter's working. That is definitely connecting to there, we know that. Yeah. Can we measure the resistance across these resistors? No, we're getting this like funny reading again, probably still a little bit of charge here. We read something like 6.8 meg. Now, these resistors are like 100k. So if we can get a reading on them. Yeah, I'm reading 65k or something there now, climbing up slowly. So the capacitor was charged a little bit basically. This shouldn't go above 100. It is still climbing up. And this one, about 800k. They're negative. Right, I'm going to have to take these capacitors out to get a sensible reading here. Here are the capacitors. I've made a mark on one of them. Yeah, hot ground. So this is the negative end that went to hot ground. This is the one that didn't have much voltage across it compared with the other one, which had in excess of 200 volts across it. Let's have a look with the capacitance meter. Reads close enough. I mean, the 680 is reading 580. That is fine, really. This one, about the same. That's pretty much what they read in circuit, to be honest. It's a bit difficult to measure if there's any leakage current. Think of a few ideas why I might have this problem. I mean, one is that the lower capacitor is leaky, but then I'd expect that to get rather hot, maybe quite dramatically. Well, it reads about 4.4 meg. I mean, it was auto ranging before. 4.5, 4.6, somewhere in that region. This is the one that was connected to the ground. This is the one with less voltage. What do we have? Oh, well, that one, hang on, maybe it's charged. One moment. The other capacitance meter would charge it up a little bit. Let's go again. Slightly lower than the other one. I mean, it could be breaking down under high voltage, I guess. Possibly. Let's look at these resistors now. So, can we measure them? Okay. That now reads 100k. And that reads 100k basically. I mean, they're very close to each other, so there's not a problem there. Now let's try measuring from the center point to hot ground. So this is hot ground here. This is the other end of the bridge rectifier, just reads open. And then the junction reads open. So it's not like there's some sort of low resistance there. The only thing I can think of is that this bottom one is leaking. I'm a bit surprised this one didn't blow up. But I suppose if the leakage current is low and there's nothing much else drawing any current, it might do that. From what I've seen, the fact I have like 200 odd volts across one and 25 across the other tells me that there is something very wrong here, and that would put the wrong voltage on the end of here, and that's going to have a definite effect on these MOSFETs when they start switching. That ain't going to work well. That is the sort of thing that would blow the MOSFETs up. I can't think of any other reason from what I've tested as to why they would be so unbalanced other than one of the capacitors is leaking. It doesn't particularly seem to provide power to anything else from there, and to be quite honest, it wouldn't make a great deal of sense, but hey, I didn't design this thing. I can see the two are joined together here, and this goes off over in this direction somewhere. I mean, it's got to go to this capacitor here, one end or the other of it. Okay, it has to go to that capacitor. I don't see any other tracks on this side of the board. Get this bit of glue out of the way. I don't really see anything else on here where it goes to. Well, it goes to the switch. This is the switch between the 220 and 110. You'd expect it to go to there actually. Okay, so it goes there and then it goes off to a via here. That feeds into this lot on with a high value resistor, so it's not going to pass any current that way. Let's have a look at these capacitors with the ESR meter as well, because it doesn't make a lot of sense. This capacitors seem to be okay. So this is the one that went towards hot ground. very low. This one, very, very low. So these should charge up to like about 320 volts, and I have like, well, I'd already switched it off actually when I started measuring, so I can't say exactly what I did have, but they were completely imbalanced. I mean, I had 236 on one, the 200 volt capacitors, and the voltage was already dropping. So this is your AC coming in. Yeah, we have continuity to the bridge rectifier. This is the other side. Bridge rectifier, so our AC is definitely getting to there. Then the bridge rectifier, diode junction to the positive end, which goes to the positive end of this capacitor, we know this. Negative goes to the positive of the other one. Negative comes back to this end of the bridge rectifier, and we can look at these diodes. Looks good. Looks good. So that's got to charge up to 320. And they should charge up equally. That's the thing I can't quite figure out. I don't have any more of the 680 microfarad 200 volts, but if I find an old ATX power supply, they'll probably be lower value, but 200 volts, I can stick a couple of them in. I'm not going to run the power supply. I just want to be sure that it all balances up, because this didn't make a lot of sense to me. This is the capacitor that had 20 odd volts in it. Yeah, so I've attached from my bench power supply the black lead coming in here to the negative end, and then with this blue lead to the black meter probe on my multimeter with some volts. Then the red lead from the power supply, the positive, comes into this resistor, passes through the resistor onto the positive end of the capacitor, so the capacitor is charging via this resistor, and I'm also measuring the voltage on the capacitor. So if I increase this to about 10 volts, you see 9.8, 9.8, and we have 19.6, so you can see I have the sum of the two coming out, okay? And the capacitor's fine, a bit up, it's up to 30 volts now, so 15.5, 31. Okay, so the capacitor is not breaking down. Let's go up some more. It's up to 44 in the capacitor now. I'll just take it up to its maximum. So 31.5 is 63 volts in that capacitor. So that capacitor is not breaking down. It's discharging back into the power supply, by the way. That's why it drops back down again. Okay, so it's not breaking down. It's not like it won't hold more than 20 odd volts. And that means this is really, really strange. What I'm thinking is, I was just checking to see if the capacitors were still charged. Now, the main MOSFETs are not in, so that current path doesn't exist. But there's other things on here. And it seems to me that something is discharging the capacitor, and it's discharging the one connected to hot ground faster, which would make me think that something is running from that 160 volts, which should be in that capacitor. We know these things are kind of connected into there, but these high value resistors, that wouldn't really do it. So I'm going to put these capacitors back in. I mean, they test okay, both on ESR and capacitance, and that check I also made. I don't really need to do the same on the other one, because this is the one that had 220 odd volts in it anyway. So let's put these back in, and then let's just take some more measurements when the power is still applied. I'm just checking the mains wiring. This is the switch for the 240 and 120 volt, and in this position, that actually reads open. Okay, this position is the closed position, but that's not used, so we don't need to connect that. We can leave that off. That might help to balance this a bit more easily. And then we have neutral here and live I had to just balance the plate upon here, by the way, because the switch keeps switching off if I let it lie flat. Okay, so that is coming through the switch, so the switch is okay. Once I plug the power lead in, that won't switch the switch off. I'm just going to take this clip off here, and then I can just hopefully just connect that one, and this might be a bit easier. Let's see. The light bulb is there, the switch is set to limit. I've attached my black meter lead to hot ground. So this point here should be, when it's powered up, about 160, about 320. And then this yellow wire, this will be the voltage going to the chip, okay? So we'll switch this on, you can watch the light bulb, bright and then off. So the capacitors are charged, okay? So this point is reading 28 volts. What's on that end? 294. So this weird condition persists. That is really, really bizarre. But it's there, we can see it. It's time for a sanity check, guys. So I have here a scrap ATX power supply. It may actually work, I don't really know, but I'm not too worried about that, to be quite honest. I want to know that these two capacitors, and on this ones, these are 560 Mark 200, so they're not as big as the ones on ours, but we could put them in there for test purposes. At least we're not drawing a lot of power from it. But before I do that, I just want to check this, that I actually have what I expect to have. I mean, it's like you start to think that everything you thought you knew about power supplies is wrong, yeah? So let's just make sure we all stay sane. We'll solder some wires on. Let's do it so we can watch both multimeters at once. So on this one, this is the bridge rectifier. Here, the chamfered end is the positive. So that's here, which goes to this end of this capacitor. So this should charge to about 320 volts. I'll just put the meter so you can see it. Yeah, so that should go to 320 volts, and then this is the junction between the two, and then the other end goes to hot ground. Right. Light bulb should come on bright and then go dim. We can see it up in the corner there, over here, okay. Power's ready, so what happens? Bright then dim. And we have 150 volts and a 309 volts, so one is half of the other. That's what we should have. Let's take these capacitors then and put these in instead and see if it works. Or at least we have the correct voltage across each capacitor. I've connected this up the same as I did with the ATX power supply, so we have the current limiter again over there. We have both multimeters, so this one should go to 320, this one to 160 or thereabouts. I'm just making sure nothing's touching anything it shouldn't. It all looks good. So let's switch this on and see what it does now. And there is still something wrong with it. Go again. So we have $290 volts on one and 33 volts on the other. Well, we know the capacitors are good, so what's going on with this? When I was editing the main part of this video, I actually realised during that process of listening to myself on my own video that I'd made some assumptions that weren't correct. Some things I was partially down the right route but didn't go far enough. At least one thing I just had wrong. And I'd also taken a few more meter readings. This was all yesterday. You can see different shirt, different day, okay? I'd taken a few other readings as well and kind of figured out a few more bits and bobs about this. But the main thing I realised as part of the circuit, this part isn't doing what I thought it was, okay? I then went to bed, as I do, not really worrying about it or thinking about it, and often this happens to me, 4 o'clock in the morning, I'll sort of wake up and I'll think, I know exactly how that thing works. And I know exactly how we should test this as well. So this is something I find very difficult to teach people, is how to think in this way, how to take these meter readings and come up with some sort of sensible conclusion. But now I'm going to explain to you why this is doing what it's doing and why these capacitors go completely out of balance. The first factor, and this is something I'd measured but hadn't actually put into the video yet, I hadn't completed that part of the video, is that this isn't wired up like you would think it is, okay? The reason I thought it was wired the way I drew it is because that's how normally these things are wired up. Well, this one's different. So this is the junction of the 2 capacitors. And that, I traced to say, went to one end of the high voltage capacitor. That thing, okay? And then the other end to the transformer winding, but that's actually not true. The other end of that capacitor actually doesn't go to the transformer winding. Doesn't go there. Where it goes is the junction of the drain and source of the 2 MOSFETs. Okay, that's where it actually goes. This end connects to the transformer winding on all these pins, 1, 2, 3, 4. Doesn't connect on that one or these 2. These 2 connect together. Doesn't connect to that one doesn't seem to go anywhere, and the same with these 3, don't seem to go anywhere, okay? What we have here is something like this. So we have HT plus the high voltage, 320 volts. We have the 2 large electrolytic capacitors. Okay. This is hot ground. And then we have the 2 MOSFETs. Connected like that. And then we have the transformer primary, which appears to have 2 other taps on it, possibly. At least 1 for sure. And then when the capacitor goes here and connects to there. Okay, and there's 2 other pins that connect in here somewhere. It may be that one of them is actually at the end and this goes into a tap further down. It may not be at the end necessarily, that one, okay. And those 2 other taps on that winding, I mean, they're definitely connected to the winding. One of them goes here into this slot. It actually goes down to this resistor. It disappears into here somewhere, okay? That's the first thing. Second thing, these 2 resistors that I assumed were balancing the voltage across the 2 capacitors. They're not wired like that. So negative or positive end of this one goes to there, and that goes to there, and the 2 are in series. We measured them out of circuit and we know they're 100k, we know they're correct. So those 2 resistors are connected like that. Okay. And there aren't equivalent resistors connected across this capacitor. We don't see any here. And there are none on the other side of the board either. So they're only across the top one. Okay, I say top by the one that goes to the high voltage, positive. That's the next thing. The third thing I got wrong with this, I almost had it right, I just didn't quite get it, is this circuit. So we had here from the AC through a diode, okay, which goes to a resistor here, comes to another resistor. This may form a voltage divider. Eventually it puts a voltage on this end of the Zener, and there's a capacitor here. This is the positive end, okay. That Zener then connects to the base of this transistor and the collector of this one via this other resistor. 4.7k goes to the base of that one, and here we have emitter collector. And I made the assumption that because this is a 30 volt Zener, which I found out, if I stick enough voltage on here till it Zeners, which I did, and it stopped at 30 volts, that this will give a 30 volt supply. But I also noted that if this is an emitter follower type circuit, the power is coming in here and going out here, and we know that is going to the chip on the supply pin. That isn't doing that. What this is doing is the diode rectifies the AC. These high value resistors charge this capacitor, which takes a finite amount of time. And when the capacitor charges up to the point that there's more than 30 volts on here, this Zener diode conducts, and it puts, and I saw it, about half a volt on the base. It turns that transistor on. Okay? The emitter of this, I know, goes to ground, hot ground. So when you switch this on by having more than 30 volts here, that then via this resistor goes to the base of this one, pulls it down. This is a PNP, remember? This is the emitter. So the base goes below the emitter voltage. This turns on, and whatever power is coming here goes out here. So this is a switch. And what this circuit is, definitely is a soft start circuit. So when you first power up, it takes a few seconds for this to charge up enough to switch this on. So this is a soft start circuit. It's also quite likely an under voltage detection circuit as well. So if the AC voltage is too low, that never switches on. Okay, so that is a soft start and possibly also a under voltage detection. Where's the power supply for this chip come from? I said I couldn't figure out where it came from. It comes in here, I know this. Where it actually goes to is down here. Okay. Now, the way a switch mode power supply works, this is pretty much always, you'll have some sort of circuit that powers this up initially, gets it running, and once it is running, the switch mode transformer generates voltage on this auxiliary winding, which rectified via a diode puts power back into this. So the startup part of it powers it up initially, and then this takes over. And the startup supply can't draw enough current, or supply enough current rather, to keep that running. And that's what we have here. So this is unusual because this point here goes to the junction of the two capacitors, and then it comes into this resistor. Okay, high value resistor, another high value resistor. That then goes to a Zener diode, another one. I did mention there was another Zener here. Okay, and that voltage comes onto this transistor here. Okay, and we can see this drives the other transistor. There's also a supply coming here via this way as well, and this then goes to this diode. Okay, diode's good. So that's just startup power to this. But because of the high value resistors, once this starts to draw current, the voltage will drop away. And once it drops to a certain level, this will stop and stop drawing current. What is supposed to happen is that this secondary provides power. And if you look through the diode, there's a capacitor here, by the way. That one there. And this, we know, is a 7812 voltage regulator. So that regulates the voltage. Okay. And the voltage coming out of here goes through this diode and puts 12 volts back on there. And this takes over from that supply. Okay. Once this is running, this supply no longer needs to provide any current to that. And it keeps running. Now, normally always, this comes from HD, the positive 320 volt supply. But it doesn't. It comes from the junction of these two capacitors. That means that once this starts running, it will start to drain the voltage from the capacitors. So that's what's happening. The soft start takes some seconds to trigger. This is almost certainly why my MOSFETs didn't blow up for a few seconds, and then once the soft start came on, this started driving, they did blow up. Okay. And this circuit, because I've disabled this, this can never start. So this just drains the power from here to such a point that the voltage here, which was about 8 volts, because it's coming through this various bits of circuit, okay, the voltage here, which is about 8 volts, is also there, gets so low that this switches off and stops drawing current. So that's why the voltage on this is going down to about 30. Quite why this one does not explode is something I'm not 100% sure of. And this point is also connected to there. So the current that's going through here into here is coming via this 1.3k resistor. And at the sort of voltage we have, starts off what, 160 volts? Yeah, that's quite a bit of current. It could, initially at least, until the capacitor starts to discharge, as much as 160 divided by the resistance. Yeah, 50 milliamps. Okay, that's what's happening to our capacitors. And the fact that this is using a 7812 voltage regulator with a heat sink on suggests A, there's quite a big voltage drop across it. Okay, coming from this secondary, quite a higher voltage than 12. And B, that it is passing something like 50 milliamps because this is dissipating some power. Yeah. So that's how the power supply actually works. Now we know that we can put something a bit more than 12 volts in here, okay, with our bench power supply, isolated from the mains, I will say, and we can power this up from the mains without these in. The soft start should kick in and this should run, and the voltage on the two capacitors should be balanced. Okay, so that's how it works, guys. I'm guessing some of you figured this before me, but hey, this is not really a race. Yeah, it's more about getting to the destination. Okay, this is a very long one, so we'll leave it there and we will try this in the next video. What I really want to see is, once I put the power in here, does this give a nice drive into the MOSFETs? And if it does, then most likely they were just fake. Hope you enjoyed that. I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.